Hey guys, welcome back. We're talking about solids in this one. All right, and basically the solid properties. So we already know a solid is a definite shape. We can write that down. And volume. Right, they're not compressible. I think that's an I, isn't it? Yeah. All right, so okay, that we know that. But some of their properties, and what properties are we talking about? Are we talking about melting point and vapor pressure? Right? And if they are amorphous or crystalline, depend on the intermolecular forces. So what forces are present? So if we look at melting point, all right, if we have strong intermolecular forces, right, we are going to have that leads us to a large or higher melting point. Yeah, MP, melting point. Right? Where we have weak intermolecular forces, it's a lower melting point. All right, so something that has very strong intermolecular forces will have, like ice actually, for a molecule that weighs 18.02 grams per mole, water actually has very strong intermolecular forces, so it actually has a relatively high melting point compared to compounds of the same size and weight. Same size, yeah, same weight. All right, so that's what we're talking about there. And then we talk about vapor pressure. If we have strong intermolecular forces, right, we're going to have a low or lower vapor pressure. And if we have weak intermolecular forces, we're going to have a higher vapor pressure. All right. So then we talked about type of solid, amorphous, and crystalline. What's the difference? Well, amorphous solids have no long range order, right, of atoms. Right? So an example of that is glass. Most of the silicates, like, right, SiO2, and some other things in there, if it's Pyrex, or which is borosilicate glass, or some other stuff, right? They don't have long range order. They have an order to them, but it's not long range, right? Whereas crystalline solids have long range order of the atoms, right? And because they have a long range order, they actually have something, they're broken down into unit cells, right? Which is the basic repeating structural unit. Okay. Now there are 7 types 7 types of cells. Now, with that, before we go into that, let's talk about, well, yeah, we'll go into this first. We'll do the 7 cells, and then we'll talk about how we get them. So here's the 7 cells. All right, and so obviously the blue dots are atoms. That's an atom down in there, right? It's just, you can't, it's like in the back, right? And so there's A here, right? Those are all A's. We're going to call it side A, or edge A. That's edge B, right? And then we got edge C, are the vertical ones, okay? So when we talk about the edges of a unit cell, those are the 3 edges. Then you got angles. Angle A here, or alpha in this case, Bravo, right, and gamma, right? From our military people, we don't call it Charlie, we call it gamma. We use the Greek alphabet. All right, so the simple cubic, it's a cube. So A, B, and C are the same. Alpha, beta, gamma are the same, all 90. Tetragonal, you kind of elongate it, right? So C here, right, the C's are longer, right? This still is a perfect square up top. It's just longer. Then we get orthorhombic, all right? Everything's still 90 degrees here, so that's 90 degrees, right? Those are 90 degrees. Everything's 90 degrees. It's just none of these sides, none of the edges are the same length. Rhombohedral, right? You take the simple cube and you just move the top. Instead of being, vertical here, we slid the top over. Kind of fun. Monoclinic, where A, B, and C do not equal each other, right? One of the angles is not 90, but the other 2 are. Triclinic, it's the same side. A, B, and C are all the same, but none of the angles are the same, and they're not 90. Hexagonal, which is a very common one, you got a hexagon, right? And then so all the sides of the hexagon are the same. It's just how high the hexagon is different. And so, of course, you have 90-degree angles, except for inside the hexagon. Inside the hexagon, the internal angle is 120. And so those are the 7 kind of, those are the 7 unit cells that our book talks about. Now, when we talk about a unit cell, all right, and we're going to do here, and we're just going to duplicate this. There's another one, there's another one, and there's another one, all right? So the unit cell I'm talking about is, and we'll just change that to a blue. There we go. I don't know if you can tell it's blue. Not really. We'll move it just ever so slightly. There you go. Oh, nope. Let me try again, guys. Sorry. Bear with me. There we go. All right, pretend that's touching. So if we dive in here, if we take an atom, again, right, this atom, right, I can put it in spots. All right, and if I take this atom and put it inside, well, what fraction of that atom is inside the cell? All right, so if you're inside the cell, you are 100% inside the cell, or the fraction 1. 1 atom completes to that blue cell. You can be on the face. All right, so if I'm on the face, if I'm down here, there's a face. So if we're on a face, half of that atom is in a cell, and half of it is not in a cell, right? So it's 50%, right? Which 1/2. So half the atom. It could be on an edge. All right. So if, well, oh, no. If we're on an edge, right? If you look, if we're on an edge, right, only 25% right? Or 1/4. Now the last spot it could be in, right, is a corner. Like this one's a corner, or this is a corner, right here, right? Those are corners. And so when we talk about corners, they're in, if I move the blue one back down, all right, the corner is in 4 cells down here. But it's also in, right, the cells above. So if I zoom out on the simple cubic here, here is a corner, all right? So there's going to be a cell here, there's a cell back there, there's a cell there, right? Those are your 4 cells. But there's also a cell up top and more cells up top, right? So this is actually going to be in 1, 2, 3, 4 down here, and then above 5, 6, 7, and 8. It's actually going to be in 8 cells. 8 cubes can go together in that corner, all right? So a corner is 12.5%, or 1/8 of an atom. So these are the atoms per cell based on location, right? So if we are inside the cell, the whole atom's inside the cell, right? If they're on the face, right, edge, corner. So what are these? So we got inside, that's a face, right? There's an edge, and then obviously the corner is the top or bottom of the edge. Okay, so that is kind of how that works. All right, I don't have a great animation for you, but that's kind of how it works. Now, if we zoom back out, come down here, all right, we're going to focus on in this course 3 different types of solids. First is simple cubic. All right. Then we'll have body centered cubic and face centered. All right. And so this, right, simple cubic. Sometimes they do it SCC, BCC, and FCC. All right. Okay. So what are these? Well, these are simple cubic is this one right here. This is simple cubic. That's what, nice, right? And so if we do this, here, let me draw that real quick. And so you'd have, right, just, oh, come on. There is your simple cube. All right, there's your simple cube. Okay. The edge of this, all right, okay, all right, would be edge equals 2 times the radius of the atom, r. And so what do I mean by that? Well, in simple cubic, you're going to have 2 atoms, all right, you're going to have an atom, nope, undo, and an atom. And if I could draw them better, you would see that they would touch on the edge. So their radii would touch. You'd have a radii here, and you have a radii here. So the edge is 2 radii of the atom, or the diameter of the atom. So 2r, okay? If, and I'm going to kind of cheat here. All right, we got to do some erasing though. Body centered looks just like face-centered, except there's some differences. Inside, you are going to have an atom inside the cell. So if I show you this way, we can do that. We just fill it in. So that's inside the cell. Then you'd still have your... Oh, we don't want to fill those in, though. We'd still have our... No. We'd still have our atoms on the corners, so to speak. But in this case, because there's one in the middle, right, it's not going to work so well, right? There's going to be a gap there. There's a gap. So, again, my picture's not the best. You'll find better pictures in your book. But the actual way to get the radius is from diagonal to diagonal. You can't hardly see that. Let's make this a little bit thicker. Diagonal to diagonal. Right? And there are going to be 4 radii on the diagonal. Okay? Because you're going to have a radius of the corner, the diameter in the middle, and a radius in the corner. All right? Now, I know my circles are not showing that they touch, but that's how it really touch. And so the edge of the body-centered cubic is going to be equal to 4 times the radius divided by the square root of 3. All right? And finally, face-centered. Here, you have atoms on the face. All right? So you're going to have atom on the face. So this atom is going to be on the face. All right? And so they're not going to be quite touching on the edge, right? There's going to be a gap there, right? But there's going to be some on the face. So if we have there and we have there, all right? Oh, that's not an ellipse. Let's try to make it a little bit better. Perfect. Now the orange circle should be the same size, but it's not in this case. And so right here, you have R, 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 and R. So you have 4 radius again. And so the edge, all right, would be equal to R, the radius, times 2 times the square root of 2, because that's a 45, 45, 90 triangle. All right, so if you know your geometry, we got a 45, 45, 90 triangle in face-centered. We got a 30, 60, 90 triangle in body-centered in a cube, and then it's just the edge of the cube. So those are the cubic structures and for the problems we're going to deal with. All right, and so we're going to dive more into this in a few minutes. Next video, whenever you watch it. If you have any questions, make sure before you look at your textbook to get maybe better pictures than I can draw. And then don't hesitate to reach out. And we'll see you next time, guys. Bye.